Hello. In this video, we will go over how eigenvectors play a role in linear transformation. So this will be linear algebra, eigenvectors, and linear transformation. Our goal is to understand the matrix factorization A equals P times D times P inverse as a statement about linear transformation. So the matrix of a linear transformation. Oops, here. Yes, let me read the matrix of a linear transformation. Let B be an n-dimensional vector space, W and M a dimensional vector space, and T any linear transformation from V to W. To associate a matrix with T, choose ordered. So choose an ordered base, B, and C for V and W respectively. So here's an example of a linear transformation. The matrix A is the matrix for T that maps to Rn to Rm. So Rn to Rm. So this is Rn and then this is Rm. Um, B is the basis for V, and C is the new basis for W. So yeah, let's do an example. Like this sounds like confusing, but once you do an example, it actually makes sense. Okay. Okay, so let's talk about algorithm algorithm for finding B matrix. So what you would do first step is compute the images of the basis vector T B vector 1, comma TB vector 2, etc. And then step 2, you would convert step 2, convert the images into B coordinates vectors. Okay. And then step 3, place B vectors into columns of TB. And then let B be the basis of B1, B2, Bn. What we want is A times B1 vector B equals T B1 vector C. And A of B2 vector B equals T B2 vector C, etc. Okay, so T transforms B into terms of C. M is the matrix for T relative to B and C. So T of X equals M of X B. Recall that vector X is equal to PB of X of B. So you're going to take and multiply B and transform it in terms of C. So here's an example. Let D equals the vector D1, D2, and F equals F1, F2 be basis for V and W relatively. Let T, a V goes to W, be a linear transformation with the property below. It says find the matrix. Oops. Find the matrix for T relative to D and F. So we got to find the matrix for T relative to D and F. How do we do that? Okay, so let me re let's go to let me read the problem again because sometimes you have to reread it again. Um, so in this example, let D equals D1, D2, and F equals F1 and F2 be basis for V and W respectively. Let T of V goes to W be a linear transformation with the property below. Find the matrix for T relative. Find the matrix for T relative to D and F. So what we're going to do is first we're going to find D1. So we're going to find T of vector D1. So that's going to equal to 2 times F of 1 minus 3 of F of 2. Then what we've got to do is find T of vector D2. And that's going to equal to negative 4 F1 plus 5 F2. So your answer is going to be okay. So my M is going to be the vector 2, negative 4, negative 3, and 5. See how we transpose this? So imagine this vector transpose, and that's how you got 2, negative 3. And imagine this vector being transposed, and you got negative 4 and 5. So this is our answer. Okay. Let's move on and do another example. Okay, so example says let B equals B1, B2, B3, and D equals D1, D2 be bases for V and W respectively. Let T, let T of V goes to W be a linear transformation with the property below. Find the matrix for T relative to B and D. So I kind of did this one already. Let me read the problem again. Let B equals B1, B2, B3, and D equals D1, D2 be bases for V and W respectively. Let T of V goes to W be a linear transformation with the property below. Find the matrix for T relative to B and D. So T of B1 equals to 3D1 minus 5D2. And basically you just transpose this vector, right? So this is how you got this 2 by 1 matrix, right? You transpose this one. It was originally 3, negative 5, and then you transpose. That's going to give you 3, negative 5, right? The same thing here. T of B2 is negative D1 plus 6D2. And then if you transpose this vector, this is invisible negative 1, you get negative 1, 6. B3 is 4D2, which is when transpose is 0, 4. And then when you put it all together, you get this matrix. Whoops. You get this matrix. 3, negative 5, negative 1, 6, 0, and 4. Okay, let's do the next one. If B and C are bases for the same vector space V, and if T is the identity transformation T of X equals vector X for vector X in V, then the matrix M is just a change of coordinates. Matrix we've learned in the last unit. So linear transformation from V into V. Okay, so now let's talk about linear transformation from V into V. In the most In the most common case where W is the same as V, and the basis for C is the same as V, and the basis for C is the same as B, the matrix M is called the matrix for T relative to B, or simply the B matrix for T and is denoted by the T transpose vector T transpose to B. The B matrix for T um, is something like this. V goes to V satisfies T of X transpose to B is equal to the vector T, the B matrix for T, and then this is the coordinate vector. So we're going to use this on the next example. So notice the similarity of vector x is equal to PB times vector x transpose to B. Okay, let's do an example. So let T equals P of 2 goes to P of 4 be the transformation that maps the polynomial P of T into the polynomial P of T plus T squared P of T, P of T, right? Part A says find the image of P of T equals 2 minus T plus T squared. So let's do this one. So look at this example. Let T, a P of 2 goes to P of 4, be the transformation that maps a polynomial P of T into the polynomial P of T plus T squared PT. Find the image of this. So you're going to get P of T goes to vector P of T plus T squared of vector P of T, and that goes to T of vector P equals to 2 minus T plus T squared plus T squared times 2 minus T plus T squared. And that equals to 2 minus T plus T squared plus 2T squared minus T cubed plus T4. So T of P is equal to 2 minus T plus 3T squared minus T cubed plus T4. Okay. So that was part A. We found the new image, which is this. Okay, let's move on to part B. Part B says show that T is a linear transformation. Prove three conditions. Condition one, zero factor. Condition two, scalar multiplication, preserve, and condition three, addition is present. So let's start with condition one. We gotta prove it's a zero factor. So yeah, this would be P of T equals to P of T plus T squared of P of T, where T equals 0. And then if you plug in 0, it should spit out 0. So yes, that is how you know it's a zero factor. Let's do condition two. Condition two, we got to prove it's a scalar multiplication preserve. So we got to do T of C, P of T equals to C vector P of T plus T squared of C vector P of T equals to C. And then equals C of T. Okay, let's do three. So condition three, we got to addition. We got to prove that addition is present. So that's going to be T vector P of T plus vector Q of T is equal to P of T plus Q of T plus T squared P of T plus Q of T. And then that's going to be equal to P vector P of T plus vector Q of T plus T squared P of T plus T squared Q of T. And then that's going to equal to P of T plus T squared plus Q of T plus T squared vector Q of T. And that gives you the same, that gives you back to this. So when you do the algebra, this is what you get. T of P plus P of Q. So you're back to here. So that means it's preserved. Nothing has changed. Okay, let's do another one. The next example says let T of P of 2 goes to P4 be the transformation that maps a polynomial P of T into a polynomial. So P of T plus T squared PT. Now find the matrix T relative to the bases of 1, T, and T squared. So my B1 is 1, my B2 is T, and my B3 is T squared. And now, yeah, so let's find the image. So the image is P of T equals 2 minus T plus T squared. So T of P is basically this 2 minus T plus T squared plus T squared times 2 minus T plus T squared. And when you FOIL out this T, you get this. So T of P is this. And then what we're going to do is find the P of T. So P of T is equal to T squared plus P of T. And then you're going to find T of B1. So if you recall, B1 is 1. So it's going to be T of 1, right? So B of 1 is equal to T of 1, and then that's get equal to 1 plus T squared plus 1, right? Here's our, yeah, so they use, so let me show you what they did. They use this matrix and then not this vector, and then wherever they plug in B of 1, which is basically 1, so wherever you see a T, you get 1. So it's 2 minus 1 plus 3 times 1 square minus 1 cube plus 1 to the fourth, right? And this is what you get. And then T of B of 2, we know that B of 2, oops, B of 2 is T. So when you do that, you get this vector. And then B of T of B of 2, we know that B of 2 is, what's B of 2? I mean, B of 3 is, and then B of 3 is T square. And then when you do the transpose, you're going to get this matrix, a 5 by 3 matrix. Okay. Okay, so now let's talk about linear transformation of Rn in implied problems involving R raised to the n. T usually appears first as a matrix transformation, so vector x goes to A times vector x. So if A is a diagonalizable, then there is a basis for Rn consisting of eigenvectors of A. Diagonalizing a matrix A amounts to finding a diagonal matrix representation of vector x goes to A of x, right? So theorem, suppose A equals P times D times P inverse, where D is a diagonal matrix, n by n matrix. If B is the basis for Rn formed from the columns of P, then D is the B matrix for the transformation vector x goes to A times vector x. So similarity of matrix representation, if A is similar to matrix C and with A equals P times D times P inverse, then C is the B matrix for the transformation of vector x goes to AX when the basis V is formed from the columns of P. What does that mean? It's a lot of information. So basically, A equals P times D times P inverse, and D equals P inverse times A times P inverse. Then vector T transpose to B is A inverse times A times P. So B matrix is the T transpose to B, and then we got to find the basis for B, so find P matrix. So let's do an example. So on the example, find the B matrix for the transformation. Find the B matrix for the transformation. X goes to A of X when B is B1, B2. So my A matrix is this 2 by 2 matrix, and my vector B is this 3 by 1 matrix. And then my B of 2 is this, not 3 by 1, 2 by 1. And then my B2 is 2 by 1 matrix. So the me we got to find the B matrix for the transformation. So how do we do this? So what we're going to do is to find the B matrix of this for the transformation. We know we're going to use this. We know that T transpose to B is equal to P inverse of AP. Oops. So that means P equals uh 3, 2, basically vector B1, B2, right? P is going to equal to uh 3, 2, -1, 1. We got it from these two B vectors. And then we got to find P inverse. So how do you find the P inverse of this 2 by 2? It's really simple. You just if it's a 2 by 2, it's really easier. You just take the D, it's equal to 1 over determinant P, and then I think you flip these, right? Yeah, so this is going to be what? Yeah, you switch these. So this is going to be 1, 3, and then this is going to be -1. uh, Wait, is that right? No. Oh, so wait, I remember. It's like this. D minus C -B A. So yes, you do flip 3 and 1. So now this is 1 and 3. You've you keep these the same, but the only thing is you make them negative. So this is going to be a -2, and now this is going to be a +1. That's much better. So my P inverse is equal to 1 over the determinant P. So how do you find the determinant of a 2 by 2? It's just the major minus minor. So it's basically 3 times 1 minus -1 times 2. So this is going to be 1, -2, 1, and 3. And when you put it all together, that equals to 1 over 5. And then this is going to be 1, -2, 1 to 3. Okay. Okay, so my T B vector is equal to P inverse of A times P equals to 1/5 of 1 to -2, 1 to 3. And then this is going to be times it by A, which was the A was that was given. That was -1, -2, 4, and 3. Right? That was given. And then times it by P, which was the vectors of B1, B2. So that would be 3, 2, -1, and +1. You can leave it like this, or you could put this all in a calculator, but this is your final answer. Okay, let's do another one. So let's do this example. It says define T of R2 goes to R2 by the T of X equals AX. Find a basis for B for R squared with the property that TB is a diagonal. So we're given this A matrix, this 2 by 2, which is 5, -7, -3, 1. B matrix is D, and the P matrix is the eigenvector. So what are we doing? We gotta define T of R2 goes to R2 by T of X equals A times vector X. Find the basis for B for R square or 2, 2D with the property that T of B is diagonal. So what I'm going to do first is I'm going to first find the determinant. So this is easy. The determinant of A is a 2 by 2, so this is going to be 5 minus lambda, and then -3 stays the same, and then this is -7, and then 1 minus lambda equals 0. And then it's easy to find the determinant of a 2 by 2. It's just this times this, major minus minor. So it's going to be 5 minus lambda times 1 minus lambda minus bracket, and then -7, -3. That equals to 0. And whoops. And when you put it all together, let's see, -7 times -3 is positive 21, and then you have a minus, right? And then when you FOIL this out, this is going to be 5. Whoops. When you FOIL this out, you're going to get 5 minus 5 lambda minus lambda plus lambda square, and then set it to 0, and then clean it up. When you clean this up, we're going to get lambda square minus 6 lambda minus 16 equals to 0. And then what we could do next is factor this out. So this is going to be lambda minus 8 times lambda plus 2. So 0. And then our two lambdas is going to be positive 8 and lambda equals to -2, right? Okay. Then what we got to do is find our D. Okay. So our D is going to be uh, okay. So right here. So now I got to find my D, which is basically the T, the vector T transposed to vector B, transpose B. So that's going to be is 2 by 2 matrix 8, 0, 0, -2, right? Okay. Then what I'm going to do is step 2. Uh, I'm going to plug in when lambda is 8. Okay, so when lambda equals to 8, I'm going to get this. -3 minus 7, -3 minus 7 augmented to a 0. Right, so if you go back to basically what I did was go back to here and plug in lambda for 8, and that's how I got that. And then I augmented with 0, and then uh, you can use a calculator, and then when you row reduce, you're going to get this matrix 1, 0, 1, 0, augmented with 0, 0. And this is going to be my x1 column. This is my x2. So my 1x1 plus 1x2 equals 0. And when you actually solve for x1, you get negative x2. When you solve for x2, you're going to get x2, and you get -1, +1. Okay. Then what we're going to do is figure out when lambda equals to -2. And when you do that, you get 7, -7, -3, +3, augmented with 0, 0. And when you do row reduce using a calculator, you get this matrix. 1, 0, -3/7, 0, -0, 0. This is my x1 column. This is my x2. So my x1 is 3/7 x2, and my x2 is x2, and I get this matrix of 3/7 and 1. So my P matrix is basically at these two vectors, right? 3, 7, 1, and what was the other one? -1, 1. My P matrix is going to be this. -1, 1, 3/7, 1, or you could think of it as this. You can like on this one, like this one, if you don't want the fraction, you can multiply both sides by 7 or factor out of 1, 7, and you would get this matrix. So my basis is okay, so that is my answer. That's my basis. Let's do one last example and then we'll just end it here. So the last example says find the B matrix for the transformation of vector x goes to A times vector x when B equals B1, B2, B3. And we are given this. The matrix A, which is this 3 by 3 matrix. And then we are given these three vectors, B1, B2, B3, or this 3 by 1, 3 by 1, 3 by 1, right? So what we got to do is find the B matrix. So how do we find the B matrix is basically this. It's T through T transpose to B is basically P inverse of A times P. So we know our P, what was our P? Our P is the A. No, P is, it is, um, so my P inverse is going to be this. Oh, so wait, my P matrix is basically this B1, B2, B3. And then if you do the like the put it in the calculator to find the P inverse, you're gonna get this matrix. So it's 2, -2, -1. I put it in the calculator because I cannot show you. It'll take too long, right? Right. So basically it's this P matrix. If you combine all these and take the inverse, you get this. My A matrix is given. It's this one right here. And then my P matrix is basically these th three vectors, right? And when you do all the ma algebra, or when you put it in the calculator, you get this 3 by 3 matrix. 8, 0, 0, 3, 1, 0, -6, 3, and -3. So my TB is this. Okay, so that's my final answer. Okay, we're going to stop here, and I think the next video will be about complex eigenvalues. Okay, yeah, I'm going to stop here.